Hi, my name is Paulo Ranazzi. I'm a postdoc at EPIC, and today we will see an overview of data augmentation in generative adversarial networks applied to the generation of geological models. First, talking about the problem statement, there exist some limitations in the applicability of the iterative ensemble meter, mainly when it is applied to complex hydrocarbon reservoirs. Today we will discuss a way to mitigate the limitation regarding the Gaussian assumption in his formulation. And the main approach is apply some kind of reparameterization to make possible the application of the iterative ensemble meter when a given parameter is non-Gaussian. And there exists several methods to do this. For example, the pure Gaussian method applies some kind of normal score transform, level set methods, and etc. In the last years, deep learning techniques have gained its attention to perform this reparameterization, like the application of autoencoders or deep belief networks or generative adversarial networks, also called as GANs. There exist several papers about this in the petroleum literature. The first one is this one published in 2017. And an interesting paper is the work from Bao in 2022 that compared GAN and a variation of autoencoder in a data simulation problem and concluded that the autoencoder provides better data simulation results, but GAN results in more realistic realizations after the simulation. However, some questions remain open. One classical example is that GANs need a large dataset to ensure a high-quality training. An example is this paper from Cajas that proved that CFAR10 is a dataset with limited size, even with 60,000 of samples to train a style GAN. And in the field of data simulation, the typical size of an available dataset can be prohibitive to train a GAN properly. And moreover, it's not always possible to utilize geostatistical software to generate additional reservoir realizations. For example, when your ensemble is provided by a third party. And data augmentation is the main approach to mitigate these effects in deep learning. Data augmentation aims to artificially increase the size of your training dataset. And some examples are geometric transformations, color space augmentation, mixing images, or even use a GAN itself to generate new samples. Now we will discuss a bit more about GANs. What is a GAN? GAN is a structure composed by two networks in a two-player game between them. A network called discriminator, who tries to distinguish between real and generated samples, and a generator, who tries to generate real-like samples from a random weighted vector Z. The optimization problem can be explained by this minimax problem. A common choice is to replace the log 1 minus d by minus log d in the generator part to avoid vanishing gradient problem. But GANs, data augmentation GANs remains in its initial stage because applied augmentation in the original dataset explicitly forces the generator to reproduce the augmented distribution. Some authors call this phenomenon as leak augmentation. Some methods has been developed to apply augmentation, especially to GANs, mainly introducing the concept of invertible transformations. But their effectiveness, its behavior has not been well studied in reservoir problems. Probably the more robust method is the adaptive discriminator augmentation, also called ADA. The main assumption in this method is that if an augmentation transformation is invertible, the generator will learn to reproduce the original distribution if the augmentation is applied before the data that are fed into the discriminator. Or mathematically, if A represents a generic invertible augmentation, there will be a unique generated distribution I that satisfies the following relation. And moreover, authors also stated that the composition of invertible transformations remains invertible, where the operator can be called from as the following equation. And besides that, a broad spectrum of transformations can be made invertible by applying them with a probability p, resulting in the following augmentation pipeline. So Here we can see the GAN workflow with the ADA, where in the adversarial training, the discriminator parameters or rates are updated using the discriminator loss, while the generator rates, that's represented here by the red squares, are updated using the generator loss. And when ADA is applied, both real and generated samples are passed by the augmentation operator before that they are fed into the discriminator. Moreover, K has showed that discriminator's output is a reliable indicator of overfitting, and they used it to make the augmentation probability adaptive over the training. They used the accuracy of the discriminator on real images, where this RT represents this accuracy, and its value range between -1 and 1, where 1 represents complete overfitting, because in this case all images are considered as real, and in this case the gradients vanish or become inaccurate. They also use an integral control to tune the augmentation probability, following the consideration that when RT is high, augmentation must be increased, and when RT is low, augmentation must be decreased. They use an integral control to control this probability, following this equation, where R target is the desired target value, and L is the proportional gain. However, in this work, we decided to use another controller because with the previous one, we experienced some high variances in the probability and the discriminator accuracy, and this resulted in the leaking behavior. So we decided to apply a proportional derivative controller, that's represented by this equation, where now we have these both parameters, k1 and k2, that represents the proportional and derivative coefficients. Moreover, evaluate GAN performance can be a challenging task. Nowadays, the most used method is the Fresher inception distance, that uses the coding layer of the inception model, and then computes the difference between real and generated datasets using this distance between coding outputs. However, FID poses some challenges due to the inception model. One of them is because the large size of the images used to train the inception model. There are 3 channel images, and usually the reservoir are built using a single channel, a single value. Moreover, the large number of parameters, that's around 21 million, can result in computational overheads. So we decided, motivated in other studies, to replace the inception model by a reservoir classifier network trained using reservoir models, and that resulted in significantly less computational power required. And then we named this metric as Fresher reservoir distance. We evaluated the data augmentation in GANs. In the Stanford 5 three-phases training image, we generated 8,000 realizations with size of 40H by 40H. Here we can see the training image in the right and some random realizations from the training dataset. We apply the non-saturating GAN with discriminator regularization to improve training stability, and we applied zero-centered R1 gradient penalty. For all cases, we trained GANs to a total number of iterations of 150,000. We used an algorithm with these parameters and used a batch size of 32. So this is the loss functions used in this work. We used a base number filter of 32. We used convolutional blocks in the downsampling and resize convolutional blocks in upsampling to avoid some checkerboard artifacts. And we applied batch normalization to each layer of the generator only, because when we use discriminator regularization, we cannot apply batch normalization in the discriminator because the optimization problem is no longer valid. And as a common practice in GANs, we didn't apply batch normalization in the first and last layers of the generator. We we apply the data simulation experiments in a toy model, considering facies indicator as uncertain, where the porosity and permeability depends of the facies. We build a production system with 9 producer and 4 injector wells, with monthly measurements, with a total period of 10 days. And we consider the measurement errors of 10% of the measurement value, with a minimum value of 1. Because we are testing the performance of each GAN, we decide to use an ensemble size of 2000 to reduce the effects of spurious correlations. We apply the ESMDA with 8 iterations with constant inflation factor and compare 3 cases. The reference, that is the GAN trained with 8,000 of samples, a case with only 200 of samples without augmentation, and another case with the limited sample to train again, however with ADA, with the target of 0.7, that is the best FRG obtained at the previous step. Now the results, we can see the FRG and the 4 iterations for different dataset size, and we can see even ensemble size considered large in data simulation problems might not be enough to train again without overfitting, like the case with 1000 samples or 2000. As stated by Cajas, the quality of the generator deteriorates when discriminator overfits, and we can see this when we analyze the reference case, where the discriminator outputs remains close to 0, and there exists some overlap between distributions, and the FRG decreases throughout training. And for the case with only 200, the discriminator outputs move away from 0, representing overfitting, and the distribution overlap ends and the FRG starts to deteriorate at the same time. Now we trained various GANs with different probabilities, categories, and probability values. Here, the case without augmentation are represented by the p equal 0. And we can see from the image that only bleeding and geometric transformations improved GAN training. Value and noise augmentation resulted in higher FRG values. And we can also see the leaking behavior when higher augmentation probabilities are considered. Now we tested the ADA performance, ranging the target value from 0.4 and 1, only considering the cumulative case with bleeding and geometry. And here, the case with R target equal to 1 represents the case without augmentation. And we can see that the adaptive augmentation resulted in lower FRG values compared to the best one obtained with fixed probabilities. We can also see that the PD controller was able to keep on track both RT and P across the iterations. We didn't see any high variance during the training. And when the ADA is applied, we can see the discriminator output remain close to 0. And the FRG decreases throughout the entire training process. However, we can see is lower conversion speed because the best FRG was achieved at later iteration as the value of our target becomes smaller. Now the results regarding the data simulation. We can see the data mismatch and the model mismatch that are represented by these two metrics. The first one is the difference between the simulator output and the measurements, normalized by the covariance of measurements errors. And to estimate the model mismatch, we use the structural similarity index measure, and we can see that the case with adaptive augmentation makes the results more similar to the reference case in comparison to the case without augmentation. And this effect is also can be seen when analyzing the posterior realizations, where each number represents a single realization. The fifth column represents the generator output from the mean latent vector. The Sixth column represents the mean of the generator outputs, and the final one represents the standard deviation. And we can see that the reference case and the case with augmentation becomes more similar to the reference case and the true reservoir than the case without any augmentations. So we can conclude that the adaptive discriminator augmentation resulted in an improvement in the FRG results. We also concluded that bleaching and geometric transformation resulted in best results. This is consistent with the work of Carras that used these both augmentations only. We also concluded that the PD controller showed a robust alternative to define the probability adaptive value. And in the assimilation part, the ADA resulted in better assimilation performance in comparison with the case without augmentation. We would like to thank our sponsors and organizations that make this conference possible, and thank you.